Good morning, everybody. So today we're discussing quiz 2 on basically on the math behind linear models. So it was a pretty tough one. Yeah, I think everybody would agree. And actually, the quiz notebook started with some holy war whether math is indeed so needed. Uh, yeah, it's a controversial question. Yeah. So actually. You can be a good specialist, you can be a really good developer without any knowledge of math, and still you can be, let's say, you can apply this knowledge, these development skills in at your machine learning engineer position per se. And wait, then why would you care about math, right? So it's you really need a lot of time to study all of that. But well, indeed, it's a controversial question. As I outlined in the notebook itself, it's really good to understand the machinery behind these linear models. In this sense, the course is a mixture of an academic one and a practical. So it both gives you some theoretical knowledge, some understanding of the methods that we use, and actually practical skills like kegling and applying all these models in your real tasks. So at least it's nice to understand this. So in my opinion, it's just beautiful, yeah, just like math. So it's really nice to understand what's going on, what's math is there behind all of these miracles actually. And it's also a nice step for you to, if you further plan to study neural nets. So it's like many things which are there behind logistic regression, then generalized to neural nets. A small comment. I would like you to ask your questions in mlcourse.ai news channel. So during this live session, you can use the latest thread. And let's double check that the sound is okay, that everything's good. So you can write a comment there in a thread as well. So YouTube chat might be a bit too noisy for such live streaming for me to answer your questions. So please better use this latest thread in mlcourse.ai news. Yeah, the sound is okay, nice. So let's go on. All right, so the first question was about ordinary least squares. Well, you just needed to select all correct statements. That was an easy one, actually. So the first option is that OLS is a method for estimating the unknown parameters in a linear regression model. So basically, if you just read the article, it's clear that that's true. So the whole idea of ordinary least squares is to estimate these unknown parameters in a linear model. So then with some assumptions, we applied maximal likelihood principle. But indeed, it's by definition, OLS is intended for that. The second and the fourth options were actually intended to confuse you a bit. So don't be intimidated with some wrong statements. So the second one, if we just literally follow the description, it would be minimizing the minimizing the differences between the real target, yi, and squared products of predicted values with some weights. Okay, it's just doesn't make sense. And the same for the fourth option. It's only absolute difference between the real target and the predicted target with some weight. So just some weight for the predicted variable. Okay, just don't be confused with some strange formulations. Of course, yeah, OLS works a bit different. And the third option is that OLS provides an estimator with the lowest variance among all linear and unbiased estimators if we have three conditions. If errors are homoscedastic, so their variances are the same and finite. if errors are uncorrelated and have zero expectation. So basically these are just assumptions of the Gauss Markov theorem, and yes, that's true. So in some sense, indeed, when Gauss-Markov conditions hold, then OLS provides the best estimate. So the best meaning the lowest variance, right? So if we estimate some parameter and we have very, very large variance, in some sense we just get a noisy estimate. Yeah. So it doesn't help if you learn a coefficient. For instance, how age affects salary. So if you learn some coefficient, I don't know, 1.7 plus minus 1%, it's fine. But if it's 1.7 plus minus 10, then you see you've just learned some noise. So that's why variance. So that's why we're interested in estimates with lowest variance. And in case that these three conditions hold, it's good that a simple procedure, these ordinary least squares, provides these estimates of coefficients with lowest variance. All right, let's move to the next one. So actually we've covered in the article that for ordinary least squares we actually have a closed form solution, meaning that just with our input matrix x and vector y we can actually calculate the output. What we're actually interested in, the vector of weights w. So there is a closed form solution, but why wouldn't we always use that? So the first option is that it's computationally inefficient as compared to numeric optimization method. Yes, it's true, so it's marked as correct here. Well, there is just a slight remark that it's true in almost all practical cases when x and y are large enough. So I don't know where precisely the threshold is, but for any actual data set, you'd better stick to numeric optimization, so gradient descent. For really small data sets, for some toy examples, tiny data sets, maybe due to some optimization, closed form solution can be better. But in any practical case, you would better stick to numeric optimization. So the second option is that it's computationally unstable in case of multi-collinearity. So when actually the determinant of these metrics, x transposed x, is close to zero. Yes, that's true. So it's actually these nitty-gritty details of how numeric methods work, how you actually compute this x transposed x inversed. But it turns out that to do it reliably and quickly, you need singular values of these metrics for some advanced methods like pseudo inverses. So basically, when it's the determinant is close to zero, then all the eigenvalues are sorry, not singular, but eigenvalues, they tend to infinity. And actually, in practice, it turns out that then the solution is unstable, so meaning it's prone to overflows and underflows. Yeah, so you know, we work on real computers, and to represent digits we typically use something like float 32 format, so 32 bits. Yeah, in case you've got extremely low or extremely high values, you can actually overflow or underflow, meaning that you are no longer you can no longer represent this number on a real computer. So there are many problems basically with numeric optimization in case of the determinant being close to zero. And indeed, if we have multi-collinearity, if our features correlate very, very highly, we can have this case. So the third option is that numeric optimization methods typically yield a better solution in terms of mean squared error. Just false. I don't know. No reasons for that. Well, the only thing I might think of is that if the dataset is large enough and with closed form solution you just cannot get an answer, you've got an underflow and overflow, well, then obviously you don't get any answer, and with numeric optimization, instead you'll have some answer. But in general, there is no motivation why numeric optimizations would yield a better solution. On the contrary, numeric optimization might, so methods like gradient descent can end up with some local optimum, while the closed form solution is precise. So the fourth option is that multiplying two square matrices is an operation proportional to the fourth power of the input in case of squared matrices. Well, this is not true, just because matrix multiplication is an operation which is proportional to the third power of your input size in case of squared matrices. Okay, maybe you've got some comments at this point. No, not yet. Let me check. Q10, yeah, the question is about Q10. Okay, we will cover that. All right, so let's go on. So the third option is, the third question is about maximal likelihood estimation. The first option is that OLS is the maximal likelihood estimator for any linear machine learning model. So this is not true. So as counterexample, we can have lasso regression. So actually no theoretical maximal likelihood estimation is known for lasso weights. Well, so OLS is basically just for linear regression model. The second option is true. So OLS is the maximal likelihood estimator only if the errors are normally distributed. There is a slight concern about the language formulation of this question, only if. So basically, in the article we discussed Gauss-Markov assumptions, and if we add the prerequisite that errors are normally distributed, then OLS is also not only the best estimator in terms of variance, but it's also a maximal likelihood estimator. So errors being normally distributed is a necessary condition for this to be maximal likelihood estimator. So it's not enough. It's not a sufficient condition, but it's a necessity. So when Gauss-Markov assumptions hold, then if we also require that errors are normally distributed, then OLS is also a maximal likelihood estimator. So this second option is true. And yeah, in statistics they learn a maximal likelihood principle. There are a lot of nice properties of maximal likelihood estimators in general, so it's nice that OLS turns out to be MLE in this case. So the third option is not true, so it's maximal likelihood estimation is a general technique, so it does not apply only to normal distribution, so we've seen examples with Bernoulli distribution as well. And in statistics it can be applied to basically any distribution. Okay, so we had some nice task, the fourth question. So we had Lerbon Jazem participating in some lottery. So he throws, he tries to score in a basketball game 9 times of a 10 penalty shoots. So he can actually win a bunny. So if you score 9 times out of 10, you get a bunny. And this Lerbon made 3 attempts, and the number of successes was 6, 8, and 9. Well, you probably see that it's basically the same as this example with methanol in the article, but it's a bit different. So actually, we have 3 trials. So in terms of statistics, we've got 3 trials. Each of 3 series, each of them with 10 trials. So our shoot is a trial, And in each shoot, we've got some probability of success. It's designated as theta, theta here. And the number of successes in a series, in actually 10 shoots, is governed by binomial distribution. So here it's formula. So theta here is some unknown probability of success in a single shot, and the number of successes in 10 shoots or 10 trials is governed by binomial distribution. So it's a particularly basic statistical formulation of Bernoulli trials. So we have some observations, 6, 8, and 9. And with this, we would like to estimate actually theta, so the probability of success in a single shot. So here we ask you to calculate log likelihood and to calculate its partial derivative with respect to theta. Well, actually, if you think about it, it's just the same as this example of estimating Bernoulli variable. Yeah, so in the first topic, we had an example with a binary variable. Actually, how many people remember the formula of methanol, CH3OH? And we covered how actually our intuitive assessments actually agrees on maximal likelihood in case of a Bernoulli random variable. Yeah, so if we observe that only 117 people out of 400 actually remember this formula, so for them this binary event is actually holds, is true. Then this 117 over 400, this 28%, is intuitively a really nice estimate for this probability that a random guy would know this formula. So this good intuitive estimate turns out to be maximal likelihood estimate, and actually it's just the same. So the hardest part with this task was to realize that it's just the same as the previous case. So we don't need to deal here with binomial distribution. We can just sum up the number of successes, 6 plus 8 plus 9, and we get 23. So this Lerbon guy, he actually succeeded in 23 cases out of 30. And these Bernoulli trials, actually, they are just making things more complicated. So a simple solution would be just to follow the very same setting as we had in the article. So a probability distribution for this Bernoulli random variable is very simple. Theta to the power of x and 1 minus theta to the power of 1 minus x. So x is either 0 or 1, so it's just either theta or 1 minus theta. So the probability of success is theta, the probability of failure is just 1 minus theta. And there is a nice way to actually write both at the same time with a single formula. And then we have a vector of observations, this vector x, x1, blah, 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 x30. So it's just a binary vector of zeros and ones corresponding to successes and failures. And then likelihood will be just the same. So our assumption is that all the experiments are independent. Yeah, it's actually a very strong assumption. Yeah, actually this guy might be really frustrated, and maybe the next shoot actually depends on the previous shoots. But in this assumption, we just think that all these 30 trials are independent, and then we can multiply probability of successes and actually probability of observing what we observe. So then the likelihood would be the product of 30 terms, and each of them is the probability of seeing either a success or a failure. So then it will be theta to power 23, because we've seen 23 successes, and we've seen 7 failures, so each of them is with probability 1 minus theta. So if we take log of that, we'll have a simpler expression, and then the derivative with log likelihood with respect to theta will be simple, yeah, because the derivative of a logarithm is a simple expression. So setting this derivative to 0, we get and this intuitive estimate 23 over 30. So actually the first answer is correct. Okay, so you could have not realized that it's that simple. You could have gone with Bernoulli distribution. Yeah, so treating each event as a series of 10 trials, and then we've got binomial distribution for the number of successes in 10 trials. Well, I'm not digging deeper into the details, but the result is exactly the same if by each observation we mean a series of 10 shots. So this term will be a probability to see 6 successes out of 10. So it's 10 choose 6, then 6 successes and 4 failures. And the same for 2 other events, for the second series and for the third one. So the computations get a bit more involved, but still these are just logarithms. And in the end you've got the same answer. So the whole idea here was to realize that this setting is just the same as actually estimating Bernoulli variable with the data that you have. So it's basically the same as example in the article. Questions? Okay, see you discuss question 10. Okay, we'll do it in the end. All right, so number 5, why should one regularize a linear regression model? Yeah, the question is a bit tricky because all of the options are actually correct. To avoid overfitting, to reduce variance of model predictions, to generalize better to future data, and to tackle multi-collinearity. So the first one with overfitting is true. So by tuning regularization parameters, we can actually avoid overfitting. So I've linked here a classical example with polynomial regression. Yeah, there's a very nice picture. So if you have some cloud of points and you would like to feed a polynomial curve here, so you can either choose a degree of polynomial to be something low, and then you are prone to underfit, or you find some nice degree of the polynomial, maybe the third of the fourth, or basically you can take a much more complex model, so a degree of polynomial, let's say 15, and you can actually feed almost perfectly all of the data points, but then you would regularize that, and due to regularization, you would actually succeed in avoiding overfitting. And another example is in the second part of topic 4. No, sorry. The third part, and also some nice pictures exactly on that. So with this toy classification problem, we've seen pictures of underfitting, perfect fit, and then overfitting. And yeah, if you cover this notebook, yeah, you will see that actually choosing correctly this regularization hyperparameter, we can actually avoid this case. We can actually avoid overfitting. To reduce variance of model predictions, yes, that's true. So hyperparameter tuning also helps reducing variance of model predictions. So as an example, in case of rich regression, we have nice analytical solution to that. So if lambda, so here regularization hyperparameter is lambda. So if it's set to 0, then it's just normal ordinary least squares. And Actually, I'm sorry. I start answering the fourth option, but they're related. Yeah. So if x transpose x is close to degenerate, if its determinant is close to 0, then we've got problem here. So we are inversing some matrix which is close to 0, and actually rich regression works in a way that it adds these this trace. So lambda multiplied by identity matrix. It's just we are adding this lambda to each diagonal, so to each term on the main diagonal, and it helps to make this matrix not degenerate anymore. A bit more advanced conclusion here is also that it leads to decreased variance of W. We don't. I guess we didn't cover it in course material, but if we analyze variance of W, there's also determinant of x transposed x in denominator, and so if we avoid this matrix being degenerate, we can actually tackle, we can actually reduce variance. Well, at the same time, I answered the fourth option. It's tackling multi-collinearity. So indeed, by adding this term and making matrix non-degenerate, we're actually tackling multi-collinearity, being the main reason for this matrix to be degenerate. And to generalize better to future data, this is also true. Because generalizing is not only dealing with overfitting, but we also have underfitting, so it's not the same. And by the same token, by tuning regularization hyperparameters, we can actually avoid underfitting as well. So with this polynomial regression example, this would be the first picture. Yeah, so here we underfit, but if we tune hyperparameters, then we can actually find a perfect fit. In this case, this hyperparameter is the degree of a polynomial to fit to this data. Right, so moving on. Which of the following evaluation metrics shall not be applied in case of logistic regression output compared to the target? All right, so logistic regression is a classification algorithm, not a regression one. So basically, we shall not apply mean squared error. It's a simple answer. So it's easy to say MSE is a regression metric. We've got classification here. If we analyze it further, it's much more involved. Yeah, so it's a small detour. But if we analyze MSE as a loss function for classification problem, it leads to some more problems. Like non-convex loss function, extreme predictions. So I want you to understand the difference between evaluation metric and a loss function. It's indeed a slight difference, but in principle they differ. So both can be, so let's say MSE can be both an loss function and an evaluation metric. But they differ in principle. So a loss function is something optimized by the training algorithm. So like log loss in a classification problem. So basically your machine learning algorithm turns into an optimization problem, and this criterion to optimize is called a loss function. And evaluation metric is actually how you estimate the quality of predictions. So when you finally have predictions for your validation or test set, and you can compare them to real targets, then you can actually calculate some function which we would call evaluation metric. So there is a slight difference here, and the question was actually about evaluation metric. So why wouldn't we use MSE as evaluation metric for logistic regression? Skipping this simple answer that MSE is a regression metric, well, physically we can do it, of course. So in principle, we can compare, we can calculate MSE for our validation set, just comparing the real targets yi versus predictions py, taking squares, then the sum, and then averaging. But then, actually, if we do a lot of changes to our algorithm, and so if we use it as a evaluation metric and then make a lot of changes and keep track of MSE, we still make some changes to actually minimize this thing. So actually, when we start tuning the model, so hyperparameters, model choice, or anything, still we'll be solving this problem of minimizing this thing. Well, because if we want to build a good model, then if we use in this case MSE as evaluation metric, of course we would like MSE to be as low as possible. So basically, we still be solving this this minimization problem. And so when it's actually this PI is an output of logistic regression, then we have some problems here. So if we plug in here our formula for logistic regression, yi, then turns out that this criterion it's actually not good for optimization. Yeah, so if we use it for training so it's not good as a loss function. It's a bit detour. Yeah, so if we actually use it as loss function, then we've got problems with. So this is non-convex. So with respect to model parameters W, so it cannot be well optimized just like log loss or MSE. And then the second problem is that so let's say the first problem, it's actually due to optimization. And the second problem would be extreme predictions. This is actually interesting. So it turns out if we optimize MSE for predicted probability compared to binary outcomes, then it turns out that these predicted probabilities are prone to be extreme, close to 0 or 1. We are not doing here a full mathematical analysis of this thing, but if you're really curious, it's interesting. So we'll have actually an optimization problem here with constraints. Yeah, so minimizing the very same thing. For simplicity, let's just write yi minus py, and it's all squared. But we have constraints. That all of pi's shall be greater or equal to 0, and they shall be less or equal to 1. Actually, to be honest, I didn't find a full analysis of this problem, but if you are curious, you can do it yourself. So, well, as a math task, it's called Lagrange multipliers with inequality constraints. Inequality. Turns out it's a bit more involved than just Lagrange multipliers that we covered last time when we discussed maximizing information gain, I guess, maximizing entropy. So the math here is a bit more involved. So if you're really interested how this just appears from the math itself, it's interesting. So using MSE for classification would lead to some unexpected results, and one of the beauties of the data science is that you can actually perform mathematical analysis and then see some conclusions, and then you will see this in your real task, on your real data. That's really cool. Okay, so Number 7 is really simple. We just discussed in the articles. So which of the following approaches do we use to fit logistic regression parameters to the data in hand? And we discussed its maximal likelihood estimation. Others, yeah, I don't know how to comment it. Others just don't fit. Least squared error is for regression, and others are just not approaches to fit parameters. Okay. Q5, is the answer considered as wrong if 3 of 4 options are selected? Yes. Yes, sorry, we ask you to select all correct statements, and no partial answers are actually supported. The question is, what if we use MSE for the logarithm of odds ratio on interval from 0.2 to 0.8? Well, still as a loss function, it leads to this problem with non-convexity. And maybe I don't fully understand the questions. So if we just restrict probabilities to be from 0.2 to 0.8, well, the problem would still be the same. So in this setting, the model would be prone to extreme predictions. So first of all, this restriction sounds weird. Why would we restrict this interval of possible probability predictions, and still they would be extreme? All right, number 8 is about analyzing logarithmic loss. So we've provided a simple equation in terms of margin. So as analyzed, as derived actually in the article, then log loss in terms of classification margin is a simple expression, logarithm of 1 plus e to the minus this margin. So let's draw this function. So if we have this margin as the x-axis, and here we plot loss, then logistic loss will look like that. And its formula is logarithm 1 plus e to the minus m. And remember, if margin is non-negative, then this is correct classification. So if margin is negative, then we get an error. Well, and then the margin itself is, in general, it's a product of, so it's defined for a training instance, and it's a product of the actual target and the model output. But for logistic regression, the model output would be sigmoid of W transposed xi. Okay, so am I right here? No, sorry, we don't need sigmoid here. Okay, let me correct that. So it's yi multiplied by actually the score that we get from the linear model, right? And in general, here it will be the target multiplied by some b, actually the output of the model for the input xy. All right, so if we analyze signs of these two expressions, so if the signs are the same, then margin will be positive and it will be a correct classification. And if margin is negative, it can be due to signs of these two parts being different, and then we'll have an error. All right, and then you're asked to actually analyze this function. Well, it's moderately simple. You're asked to calculate derivatives and to pick correct statements about this function. Okay, again, this trick that all of the options are actually correct. So the model is penalized, so meaning that this loss is positive, even in case when a training instance is correctly classified. Yes, that's true. So the loss is greater than 0 actually for any argument, for any margin, as we've just seen on a plot. Logarithmic loss is a strictly decreasing function of margin m. Yes, indeed, we'll just calculate the derivative in a sec. And two more questions are about the first and the second derivative of this function. Okay, I guess it's now fairly easy for you to take this derivative. And yes, indeed, we see that it's always less than 0. Okay, let's do that. So the loss is logarithm 1 plus e to the minus m. So if we take derivative of this loss with respect to margin, from the logarithm we get this expression in denominator as a derivative. Then we take the derivative of the inner expression. It will be e to the minus m. And further we have a minus from this expression minus m. And so it turns out to be minus, and this expression is actually a sigmoid. You can recognize sigmoid if we just multiply by e to the power of m, both in numerator and denominator, then we'll have 1 divided by, so remember we are multiplying by e to the power of m, then we'll have this expression, which is precisely minus sigmoid of minus m. All right, and so we see minus and a sigmoid, so sigmoid is always greater than 0, so the whole derivative is actually always less than 0. All right, so then the third is true, so the function is strictly decreasing. And then you are also asked to analyze the second derivative. Let's do that. So we had the first derivative being minus sigmoid of minus margin. And so if we take the second derivative, then we've got, so remember a property of a sigmoid function, let's say of its argument z. So if we take its derivative, it can be expressed in terms of the sigmoid function itself. It would be sigmoid multiplied by 1 minus sigmoid. So we have this first minus, then the derivative of sigmoid, so sigmoid of minus m multiplied by 1 minus this sigmoid. Okay, it's a bit confusing, so it's really easy to confuse multiplication versus the argument. So I'll skip the argument. So the derivative would be sigmoid multiplied by 1 minus sigmoid, where sigmoid is a function of this minus margin. And then if we take derivative with respect to margin, then we've got minus here is in this part, and then it turns out minus multiplied minus 1 by minus 1, it will be a plus here. So basically we'll have this expression sigmoid multiplied by 1 minus sigmoid, and we're interested only in a sign, so the sign is positive. So meaning that the function is convex. Yes, so again, a small sketch of this function. So turns out it's always strictly decreasing. So the first derivative is less than 0, but the second derivative is greater than 0, meaning that the function is convex, so it's this U-shaped function. All right. Yes, indeed, turns out all of the options are actually correct. So number 9, we have a simple logistic regression classifier, and so here we've plugged so we have two features, and we've plugged coefficients in a linear model, so we'll have 3 of them, W0, W1, and or either it's an omega. Okay, so we'll have a formula that we model the probability of the target being equal to 1 as sigmoid of this inner product, which in case of two features it can be written as W0 plus W1 x1 plus W2 x2. And we actually know these all these W's in the task, and we are actually asked to select the correct decision boundary of such logistic regression classifier. So to choose one of these 4 options. Okay, well, let's understand what's written here. So the answer of the model would be just the sign of this predicted probability compared to 1/2. Yep. So we have a predicted probability, so it's something from 0 to 1. If we compare it to 1/2, then we can actually classify. So the binary answer of this classifier will be the sign of this expression. Okay, to choose the correct decision boundary, let's indeed plug these values that we are given, these 3 coefficients. Let's plug them into the expression of model answer. So the sign of the answer will be sign of 3 minus x2. Okay, so we see feature x1 just does not influence decision boundary at all. So we are left with figure C or figure D, right? Because so independently of x1, we'll have the same answer. It's not the case for figure A or figure B. In both of them, we have different answers for different values of x1 of the first feature. So we are left with either C or D. And so if we plug some value larger than 3 for x2, so if we take x2 being, let's say, 5, we see that the answer is the sign of 3 minus 5, so it shall be negative. So that's why we are actually left with figure C. Okay, and now this indeed controversial question 10. Yeah, I see some discussions about it in the thread. Probably I don't have time right now to read all of them, all of your comments. Okay, so basically we've linked here to sklearn example on bias variance decomposition, and we asked you to change estimators to decision tree regressors, actually four of them with different weights, 1, 2, 5, and 10. So then you'll have bias variance decomposition just the same as in the example, and you need to select correct options. Okay, so let's dig a bit into the code. So we have 4 estimators. decision tree regressors of these different depths, 1, 2, 5, 10. So we generate some synthetic data. So this is going to be our underlying function f over x. So it's just a mixture of two exponents. And then we generate several samples from this distribution. So actually the real target would be this f of this function f that we defined here, plus some random normal noise. And we'll be actually generating a lot of such sets. So yeah, in this setting we'll have 50 data sets. In each of them we'll have 50 training points and 1000 test points. And then we define this noise actually to add to the true function f over x. Okay, so when we execute that, we see that x test, let's take a look at the shape of this NumPy array. Okay, we're interested in y test here, right? So it will be 1000 rows and 50 columns. So we have 50 different data sets. Each of them is 1000 long. Okay, let me see. And x test here would be just indices, I guess. Yes, x test will be actually x's, and y's would be answers. And for the same set of x's, we'll have 50 different targets. Okay, and then we actually in a loop for all of 4 estimators. Then 50 times we fit an estimator and then make predictions. And then this bias variance decomposition, bias variance and noise decomposition is actually covered in the article. But what they do here is actually for all these combinations of 50 data sets, actually you see 2 cycles here, that this will be 500 combinations of all the different pairs in these 50 identical, so actually 50 data sets. And then they calculate the square difference between the test set and the predicted vector values. It's just to gather more statistics on the error. So divided by these and repetitions squared. So here, basically, in these 2 cycles, we calculate the error between actually all the pairs of subsets that we've generated, right? So we have 50 different generated sets of answers. They're here y predict, and we've got 50 vectors of true target y. Basically, they all go from the same underlying distribution, so we can actually compare all the pairs to gather more statistics to estimate this y error. And then noise is just the variance of this y test. So it's some true noise that we've inserted. So here we've got some analytical function f, and then we add random noise, and that's how we get y test, basically. So the variance of this true target y is actually our noise. Bias would be the squared, so actually squared bias is the square difference between the true value of this underlying function and our prediction. So actually average value of the prediction that we make. So bias means this offset, so the average value of the offset of this difference between the true true function and our prediction. And then variance would be just the variance of our predictions. And so for different values of depths, we'll have different decomposition of the error into squared bias, variance, and noise. And there are some nice pictures. So this blue line is actually this underlying function f. It's a mixture of two exponents. And our data set would be these blue dots, which are scattered around this blue curve with some noise. And for different depths, we'll have different decision functions. So for depth 1, we'll have just a step function. And we do 50 repetitions. So we'll have 50 different these red lines will correspond to 50 different decision functions. So you can see there are a lot of them. And then the average one would be bold red. So we'll have a better picture with max depth of 2, and of course much better picture with max depth of 5. And then we have some decomposition, so we can keep track of bias, variance, and noise. Well, theoretically, bias shall always decrease, and variance shall always increase with increased model complexity. So noise is something introduced which stays the same. So indeed, I asked you to fix random state parameter here to be 17, but actually the data generation process in NumPy, it has its own seed. Yeah, so it's a bit controversial here. Turns out it's actually in the example from sklearn it was 0 there. Yes, it's a bit annoying that actually in the end it affects the output. So here we see that squared bias is indeed always decreasing with model complexity. So we had really large bias for depth 1. So basically our decision tree, the step function, just didn't hit the true function correctly. That's why large bias. And bias would only decrease with model complexity. But why variance is not strictly increasing, that's a small difference. Yeah, so it's really hard to explain why precisely theoretical thing wouldn't hold on your toy dataset. I guess we need more. Actually, we need to increase the number of experiments to collect more statistics, and I guess it's a bit noisy because the training set is too small here. You can make some experiments to see if you increase it much more, whether we'll have a nice change of variance as well. But so it turns out the best fit is actually max depth of 5. So it's better than max depth of 10. And actually it's not due to decreased bias. It looks like it's due to decreased variance. But well, actually both. Yeah. So in terms of bias, it's worse than max depth 10. But with max depth 10, we've got larger variance, and that's why actually there is this trade-off between bias and variance, and max depth 5 looks like a better fit. Considering the answer options, let's run it with seed 0. I think, yeah, it affected actually one of the answers. With a different seed, we still had bias decreasing, but variance was a bit different. Yeah, so okay, here variance does not always increase as well, but still there is some dependency on this seed. So basically, going back to answer options, variance always increases with increased max depth. Well, this theoretically shall hold. In practice, we don't see it. We'll disqualify these options, so this is not going to influence the well, your credits. This part, as well as the which one? Which one was affected? Okay, definitely the first one. So the second option is that minimal MSE is achieved when max depth is set to 5. Yes, that's true. So max depth 5 looks the most appropriate thing here, the most appropriate hyperparameter. Minimal MSE is achieved when bias is also minimal. No, it's not the case. I guess it's also independent of the seed. We'll have really low bias for max depth 10. Well, this is not the best fit because the variance is larger for max depth 10. And in the picture we can also see it here. So with max depth 10, all these decision functions are sort of shaky, meaning that, yeah, there is some variance here, a bit more than for max depth 5. Minimal MSE is achieved when variance is also minimal. All right, yeah, this is fourth option is which is influenced by this random seed, which will, so that's why this option will be disqualified. So minimal MSE is achieved when variance is also minimal. Okay, this is not true for. Okay, this is dependent on the seed. As we've seen. Okay, so this is not a good answer option actually. And the tree with max depth 10 is overfitted. Yes, for sure. So it's hard to say just by itself. Yeah. So hard to say whether for specific value of max depth it's overfitted or not. But in comparison with other values of max depth, we can see that for max depth 10, indeed, we see overfitting. So just comparing these to the depth of 5, we see the effect of overfitting, that we've got lower bias, but we have higher variance, and in the end, the error turns out to be larger. That these are actually syndromes of overfitting. Yes, it's a bit pitiful that, yeah, not always such answers, such tasks turn out to be really good. So it turns out there is some randomness here due to these seeds. So we don't disqualify the question fully because it's really cool for you to understand this bias variance decomposition. But we'll disqualify options 1 and 4, meaning that the correct answers will be considered only with respect to options 2, 3, and 5. Okay, so more questions here. Yeah, I see a lot of discussions on exactly this question 10. All right. Okay, so that was quiz 2. So pretty tough, but I think now it really helped you understanding the material of this topic 4. I admit that yeah, maybe somewhere we need to improve these articles on topic 4. So some parts are really tough. and dive a bit into statistics. But I really believe that this is a solid solid understanding for you now to actually go with neural nets and at least to understand backpropagation. So maybe one of the most prominent ML algorithms ever. And it's first of all, it's just cool, and then it's also nice for you to grasp all these mysteries behind basic ML and then some simple neural nets as well. Okay, so that was it. Tomorrow is the deadline actually for the Alice competition, so catch me if you can. As I mentioned on Slack, there's a bit of confusion with these time zones, so they actually changed time tonight. So that means that, well, in any case, it will be resolved in your favor. So actually, you'll have time till 9 GMT. So till 9 new London time, 9 p.m. Okay, thanks for joining this Saturday morning, and good luck.